Working with switches on the Pico and Pico 2 is straightforward. We do have to avoid the RP2350's bug, but I can show you how to do that. Let me show you how. Hi, I'm John, your concierge to the world, the Raspberry Pi Pico, Pico 2, Robotics, IoT and other fun tech. Remember to subscribe and join the community. The simplest input sensor we can use on a Pico or Pico 2 is a switch. In this video, I'm going to look at a simple single pole, single throw switch and how to connect them up to a Pico 2. I'll use two different strategies to read the switch: polling its status in a loop and using an interrupt on the Pico 2 to notify me when the switch changes status. If you like this video and it helps your learning or projects, why not drop me a cash tip using that super thanks button below the video or the payment link in the description. I'm saving these up to get myself to the open source conference in San Francisco, and I'd appreciate your help in getting me there, and I hope to see you there too. Please hit the like button on the video and subscribe for more. This video is sponsored by PCBWay. PCBWay is there as a partner to help us as we move beyond our breadboards to put our projects onto a PCB. PCBWay engineers check out the PCB design and fabricate them into high quality PCBs, which we can then use to build our projects. Using PCBWay's website, we can select options of colours and material for our PCB and follow along the fabrication process. Trust PCBWay to build your next project PCBs. So I've got a drawer of switches as well as kits that contain lots of switches, and I'm sure you have too. So I'm not going to tell you everything about switches in this video, but let's just drill into switches that are going to be useful to connect to our Pico 2 and actually do something. So you can get switches in this momentary orientation or in latched. Momentary is basically, it only connects the contacts when you're actually pushing it. Whereas in latched, you push it to connect them and then push it to release. Generally, we're only interested in momentary for connecting to a microcontroller. Now, of course, you can also have multiple poles. So if we have just a single pole switch, then it is about connecting A to B. But we can also have a double pole switch, in which case A is either connected to B, or when you're pushing it, it's connected to C. So it's that pole concept. Again, really within microcontrollers, we're probably only talking about single pole switches. You can also have double throw, which is basically just tying multiple switches together. Again, why would we do that on a microcontroller? One pole or one throw is quite enough for us. So really for microcontrollers, I'm really only going to be talking about single pole, single throw switches. Everything else I'm going to do in software. I'm going to just use the switch in the least amount of hardware possible onto the connection to the Pico. So I'm basically just going to connect one side of the switch directly to a GPIO pad, and the other side I'm going to connect directly to ground. And I will use software configuration to do everything else. Now, there is going to be some software configuration because if you can imagine this, when you push the switch and it's closed, that's great because that GPIO port is definitely held down and to ground, and therefore we can read that as a sensible ground signal off of that pad. When it's not pushed, well, if I'm not doing anything with that pad, then it's potentially just floating, and induction and other things might cause it to actually go above the threshold and cause a signal. We can't actually have that, so we will do something called pulling that GPIO line up. That isn't quite the same as just connecting it to the high voltage to 3.3 volts. We are connecting it to 3.3 volts, but we're doing it through a resistor, and we're enabling that because that's actually a software capability that we can turn on within the Pico 2. Now, this whole concept of pull-ups is really enabling this circuit here, and we can absolutely do that by just laying that out on the board, or we can use this internal pull-up resistor to do that for us inside the Pico, which is what we're going to do. There is another model and another way of doing this called pull down, and you can absolutely do that, and you can connect a switch in a pull down model. I'm going to avoid that partially because you may remember that there is actually a bug on the RP2350, and that is all about using the internal resistor bank of the RP2350 to pull up a GPIO pad. So let's not go there, because that gets us into a world of pain and suffering. If we're using the GPIO internal resistor bank of the RP2350 to pull the line up, we don't have that problem. It's only when we use the RP2350's internal resistor bank to pull the line down do we actually get an issue. If you want to know more about how I do all of this and a bit more of the theory and the formulas for actually how to work out the values for those resistors in pull up and pull down and all of that, I've got a course on Udemy called Raspberry Pi Pico micro projects that actually talks about all of this for switches, and it looks at standard switches, and it also looks at rotary encoders, which are really quite cool switches. So please do look at that course if you're interested in a bit more detail on the theory behind this. As always, all of the code and examples that I'm going to talk about on this video are shared on GitHub in the repo here. Now, this repo has a lot of examples, and some that I've put into other videos. The ones with the switch in front of them are the ones that are actually for this video. What I'm going to do is we're going to connect our Pico 2, and we're going to put an LED connected to GP15. That's the bottom left connector point on here, and I'm going to connect that LED via a 100 ohm resistor to ground. That way it's safe, and then not too much current will be drawn through that LED when we illuminate it. And then on GP14, which is the next pin up, I'm going to connect that directly to ground via my switch. So that gives me the ability to actually push that switch to sense it by the Pico 2 and then do something with it with that LED. So let's have a look and actually put an example that's actually just going to follow what's going on that switch. Whatever happens to that switch, we'll do to the LED. So over in the repo, I've got this example called switch pole. And this is going to be to basically follow what the switch is doing and try and make the LED copy it. So this is a very simple example. It's one single C++ file. And what we're basically going to do is we're going to set up an LED. And I'm placing that external LED on GPIO 15, as you've seen, and I'm going to have a switch on GPIO 14. So the LED is an output, and then I'm going to set up the switch in the same way and set it as an input. And I'm going to use this pull up function here, which means that I basically get the free resistor to pull that line up to high. So if I read that value now with the switch not pulled, I will get a high or a true value or a 1 value from it. If I read it when the switch is pushed, I'll get a 0. So what we're going to do is we're going to go through this loop forever, and I'm using for colon to give me that forever loop, and I'm basically going to just pull back what is the state of the switch. So is it currently a high on that line, which means the switch isn't pushed, or is it a low on that line? And whatever that is, I'm going to use that to light the LED. So let's have a look at that working. So our LED is actually on, and then when we push the switch, the LED goes off. And that may seem counterintuitive, but actually it's what's going on that switch. When the switch is not pushed, that GPIO pad is high. When the switch is pushed, that GPIO pad is low. So let's do something a little bit more useful using exactly the same circuit. So we're just changing the code. So what I actually now want to implement is latch behavior. So when we push the button the first time, we will actually turn on the LED. If we push it again, we'll turn it off. Push it a third time, we'll turn it back on again, etc. This is what's called a latch switch behavior. So this switch latch pole example is basically using a polling strategy to give us this latch switch behavior. So let's have a look at main first, because what we're actually going to do is again set up our LED as an output so that we can switch it. And then I've got this latched switch class here, which is actually setting up and managing my latch switch so that I can actually just go and get the value from the latch switch and say, is the latch switch on? If it is, then or whether it's on or off, that's the value I'm going to set my LED, and I'm going to continually do that. Now, okay, this does mean that I'm setting the LED on continuously because it's in the on state, or setting it off continuously if it's the off state, but that's part of the poll process. I could put a check in there to see actually has the value that I've got back from is latched on changed, and only if it's changed, change the LED state, but I've chosen not to do that to make it a little bit simpler. So what does the latch switch look like? Well, largely it's about setting this up here with our GPIO pad, then giving it a poll routine, which is the routine that we're going to call continuously in that loop to check whether the value what the value of the switch is and whether that changes, and therefore whether we need to change the value of our latch. And then a function here called is latch on to just tell is the switch in on position or is it in off position from a latch point of view. Now we could actually ask, is it pressed? And that's actually a difference. So, you know, actually we pushed it down or not? So let's have a look at that code. So the setup of this class is the same as what we did in the switch poll example, where we were just setting this up to be an input and pulling it up. Remember, we need that pull up there to actually pull the value high. And then our poll function is basically going to look and see what is the value of the switch. Has it actually been pressed? And if it has been pressed, then we need to switch the value from on to off that we're storing. This poll function could be called multiple times while the switch is pressed, and that could be a bit of a problem for us. So we want to put a bar in here to say that actually our function only actually does something if this is the first time we've noticed the switch being pressed, or the first time we've noticed the switch has been unpressed. And so I've got a little bit of code in here with this flag expressed to try and suppress that, to mean that actually we should only do this code the first time through. And so, or the first time each time a switch is pressed. So as the switch is pressed, we will go and say, well, actually, expressed is not true, right? Okay, we can go into this, ignore its bounce for a second, and then we can basically send the pressed is true, and we can change the state of the X on. That means that we're protected. The next time through here, if the switch is still pressed, well, actually express is now true, so we can't go through that, and actually we will do nothing, and we will just ignore it. So that's how I'm making sure that even if we call poll multiple times with the switch down, until the switch is actually released, we actually don't do anything. And the release bit here, which is the bit that actually frees up the expressed, is that bit there. Now there is a problem with this, and you'll see that problem in terms of bouncing, because switches bounce, and they basically go from, when you push them, they actually don't go cleanly straight from high to low. They tend to bounce around a bit between those states, and the same when they come back up. Now that's a bit of a problem because our processors are quite quick, so they're able to actually read those bounce behavior. And that bounce behavior would mean that actually we would get hundreds of potential presses in the time that we actually just pushed it once. Now the way to avoid that is to put in some sort of bounce detection or bounce delay, and that's what its bounce does here. Basically its bounce is a little bit of a time delay process and saying, well, actually Unless it's been a reasonable amount of time since we last detected pressed, we'll actually just ignore it and say it's a bounce. So that's what I'm doing here. I'm getting how long it's been since we last had a press, and if it's been less than that amount of time, then we suggest it's a bounce, and the bounce will mean that actually we suppress and do nothing. The amount of time I've given for switch bounce is set up over here, and it's 200 milliseconds. For a nice firm UI controlling switch, that's pretty good. If you were using it for gaming, I think 200 is probably a bit on the slow side, and it would need to be a bit faster. But it depends how fast you can go, depends on how stable your switch is and how much bounce you get from switches. I have had some switches which are terrible at bouncing, but most switches these days are pretty good and not too bad. There are other approaches you can do for bounces from a hardware point of view, including adding capacitor, but that's sort of beyond the scope of this video. So our LED starts in the off position, and when we hit the button, it will turn on. When I hit it again, it turns off, and I'm doing it quite quickly there. But you see that's actually quite responsive and works really quite well as a latch switch. I wouldn't actually use this polling strategy to read a switch, well, not unless that switch was really bouncy. Most switches I would use an interrupt mechanism for, and an interrupt means basically I'm going to ask the processor itself to just let me know when an event happens on the GPIO line. And the events we can be interested in is a falling edge, i.e. the value dropping on the towards from high to low on the switch, or a raising edge, i.e. going from ground up to the high voltage. So this means that we don't actually have to keep polling to see what the status is. We can just let this actually happen in the background. Let's have a look at an example of that. The interrupt example is actually very close to what we've already seen, well, at least in the main program. So the main program again is setting up our latch switch, and it's configuring our LED, and it's still going through this loop here, but you'll notice that there is no poll in that loop of the switch now. We're just able to read the switch directly to say, is the latch on? So what's going on in the switch code? So now in the setup of this, we're not only setting its direction and putting it as pull up, we're also enabling it to call a static function when it actually sees a falling edge. So that's how that works. So that static function then, so let's have a look at what that's doing, because that's really what the difference is here, because actually our isLatchOn function is actually just returning the value of x on. So what we do in the static function is we basically go and find out where our actual object is, and I've sort of done a singleton pattern here holding a value of p self to find as a static variable to actually call back down into the object, because I'm going down into this function here. So this is a pattern I use quite regularly to go from functional or class-based static functions down into methods on an object, and that's a pattern that we need to do in order to interface with these sorts of C functions. So that's what I'm doing there, and that really gets us into here where we've actually got this data of, you know, what is the GPIO port that's that we've got this event on, and the event itself. And now all I can do is every time I detect a falling edge, basically I can switch the state of our latch. And that makes actually in some ways the code in here a lot simpler. We don't need to worry about is this a press, is this not a press, was I pressed last time the poll was called. All of that stuff that we had before goes away. We still do have the problem of bounces, and so I still have the same bounce code in here to just remove bounces, because they still will happen, and indeed the interrupt will get called potentially hundreds of times because it's bouncing. So just finally, so on the setup of this, you can see that I've actually got this static variable p self that is what I'm using as sort of a singleton to find the object, and this static function GPIO callback static, which is what is going to be called back from that interrupt function, and what we're using as setup with the interrupt function. Now there is a side effect of this, because now I can only use this once and I can only have one latch switch, and I might want lots of latch switches, and I'd have to do this in a slightly different way. To do that, I'd have to create some sort of manager class that was handling that. There's not really any point demoing this because it works exactly the same as the polling example and looks absolutely identical. Now, in one sense, that example has a polling loop in it, because the main is going around and actually checking to see the status of is latched. So that is sort of polling really. And I wanted to remove that properly, and to do that I need to do a bit more work, and for a start I need to create the concept of an action handler within our switch. So this abstract action handler I can then replace with a LED action using polymorphism, and it's that approach that I want to use then to be able to trigger the LED to turn on and off, which frees up my main routine to do whatever I want. Now what I don't like really in the interrupt example is the fact that our main loop has to still go down around doing all of that, looking for the latch state. So in this example, the switch latch action, I've actually got away from that. The way I have to get away from that is a little bit more complicated, because I have to actually create this LED latch action and let it manage the LED. So let me just explain this. So in this example, we've our latch switch and we're still setting up the same way, but now I'm putting all of the setup on my LED into this latch LED program, and then I'm telling the switch that I actually have this action and to call this action every time the latch state changes, which means now that actually our for loop, that we've still got to have some sort of for loop in the main to just keep going round, but it's actually not doing anything. We can do whatever we like because everything else is being handled through the interrupt mechanism. So this latch LED is of type latch action, which is that polymorphism that I'm using, and a latch action basically just has a virtual function on it called action, which takes the latch status of the LED switch, whether it's on or off. So that's all we've got to do in there. So a latch LED is basically just going to set this up, the LED up, and the action is basically just going to take whatever the state of the latch is. It's going to change the GPIO level to be that for our LED, setting the LED on or off. So I guess we should have a quite quick look at what's changed in latch switch, and we've got an additional function here to be able to set an action, which we're just storing it in a variable called p-action, which is of type latch action. And then all I'm doing really is every time I go through the loop and we actually need to change the value of the action, I'm just going to call action on my stored action. So that gives us the ability to actually function and to switch the LED. Now there is a caveat in this, of course, because changing a GPIO pad and therefore impacting an LED is a really quick thing to do and very easy to do, because this function does need to be very quick and not to take too long, because we are still in the middle of an interrupt call here, and we should be coming out of that interrupt as fast as possible. If we needed to do a long amount of work, or we needed to talk to some other peripheral or things, then we would need to do this in a slightly different pattern. It's just easy to do because I know that changing a GPIO pad is just a couple of instructions, and it's therefore not going to delay this interrupt. Now this whole example works because we actually can do it all from a single function in a single class on this callback, because when we enable and request a IRQ callback on a GPIO line, we can only give it one function per core for all GPIO pads. That is quite a limitation of the Pico SDK. So to get over that, you basically end up using a form of polymorphism and what I would call an observer pattern. So basically I'd end up writing a manager class which is going to actually manage and observe all of the GPIO pads and feed out observer calls to when events happen on those GPIO pads. The technique I've used here I use in lots of my projects, not just for physical key switches, but for sensing the speed of motors, the wind speed on a weather station, or perhaps the notification of a device needing attention. I'm going to do one more video on switches in the next few weeks, looking at a matrix keypad, so keep an eye out for that one. If you like this video and it helps your learning on projects, why not drop me a cash tip using that super thanks button below the video or the payment link in the description. Remember, I'm saving these up to get myself to the open source conference in San Francisco, and I'd appreciate your help in getting me there, and I hope to see you there too. Thank you very much for watching. If you enjoyed the video, then please hit the like button and please subscribe to my channel so you don't miss the next video. Bye bye for now.